Hi, I am Jenny Quinn, President of the Math Association of America, and it's my pleasure to welcome you to the final event listed in the conference program for this meeting, the Gerald and Judith Porter Public Lecture. This lecture series was established through the generosity and inspiration of Gerald and Judith Porter. Jerry is Professor Emeritus of Mathematics at the University of Pennsylvania and has served the MAA as treasurer, as member of the Board of Governors for 22 years, and as a member and chair of numerous committees. Judith is Professor Emerita of Sociology at Bryn Mawr College. Her research focused on the relationships between AIDS and addiction. The Porter Public Lecture is offered jointly by the AMS, the MAA, and SIAM at the Joint Mathematics meeting every year. Anyone interested in mathematics is invited to attend. So thank you for finding your way here to share our common interests. Today's speaker, chosen for her excellence in mathematics and exposition, is Dr. Lauren Williams. Let me introduce her to you. Lauren grew up in a suburb of Los Angeles, the oldest of 4 girls. She liked math from an early age, but also loved art, reading, writing poetry, and playing the violin. As she participated in math competitions and summer programs, she noticed there were not very many girls involved. But she credits her younger sisters, also good at mathematics, for helping to mitigate her feelings of isolation. Lauren majored in math at Harvard, spent a year at Cambridge doing part 3 of the mathematical tripos, and then obtained her PhD from MIT under the supervision of Richard Stanley. She bounced back and forth between Berkeley and Harvard, first for postdocs and then for faculty positions. In 2018, she joined Harvard as the Sally Starling Seaver Professor at the Radcliffe Institute. And in 2019, she was named the Dwight Parker Robinson Professor of Mathematics. Some of her recent awards include the AWM Microsoft Research Prize, the Rose Hills Innovator Award, a Simons Fellowship, an NSF Career Award, a Sloan Fellowship, a Distinguished Undergraduate Teaching Award, and an invitation to speak at the 2022 International Congress of Mathematicians. In addition to her mathematical successes, Lauren is a mother of 2 young children, ages 6 and 9, who bring her a lot of joy, but also make the task of balancing her personal and professional responsibilities a little more challenging. COVID, and especially the pivot required from the Omicron variant that led to this virtual meeting, have required even more flexibility from all of us. In fact, Lauren traveled to the UK, arriving today. To reduce stress and prepare for any eventuality, she pre-recorded her talk that we're going to share with you. Lauren has confirmed that she arrived safely, but she is actually unable to join us. So if you have questions during the presentation, you can put them in the meeting app with the link being provided in the chat, and they will be forwarded to Lauren, who can get back to you. And with that, it is my pleasure to present Dr. Lauren Williams talking on tropical geometry and shallow water waves.
Thank you very much. It's an honor and a pleasure to be giving this talk. I would like to thank all of the individuals who have worked so hard to put together this virtual JMM, and in particular, Georgia Bancourt, Christina Santos, and Boris Hasselblad. This lecture is meant to be a public lecture, so if you are someone in the audience who's not a mathematician, I'd like to expressly welcome you. I will do my best to make this talk as down to earth as possible. So now I will share my screen. So the title of my talk is Tropical Geometry and Shallow Water Waves. As you can see in this photo, waves have a very interesting mathematical structure. This photo was taken on a beach in Mexico by Mark Ablowitz. And roughly speaking, the purpose of my talk will be to explain how to understand the kinds of patterns that we see when shallow water waves, like those at a beach, interact. So here's the plan of my talk. I'm going to start by explaining what is tropical geometry. I'm then going to explain what is the Grassmanian. I'll then say a few words about what is total positivity. And then I will get to the main topic, which is shallow water waves and the KP equation. And in particular, I want to explain a relation between tropical curves and shallow water waves. So let me give kind of an overview of tropical geometry, and I want to start by explaining a little bit about algebraic geometry. Polynomials are expressions which are built from multiplication and addition. So for example, y minus x squared and x squared plus xy plus y squared minus 1, and x squared times the quantity x plus 3 minus y squared. These are all examples of polynomials. And now we can associate a geometric object, commonly called an algebraic curve or variety, to a polynomial or set of polynomials by plotting the points where these polynomials are 0. So for example, the polynomial y minus x squared equals 0 gives rise to this parabola. The following polynomial gives rise to this ellipse, and my third polynomial gives rise to the curve that you see in red. So these are ways of associating geometric objects to algebraic objects. So algebraic geometry is the study of these geometric objects, and the field is very old. It has roots dating back to 350 BC. There was a huge amount of work starting in the 1800s, and it remains a very active field of mathematics today. Now, let me say a few words about tropical geometry, which is much more modern. So tropical polynomials are expressions which are built from addition and also the maximum operation. So for example, the maximum of x, y, and 0 is one tropical polynomial, and another example is the maximum of 3, 2 plus x, 2 plus y, 3 plus x plus y, 2y, and 2x. So this is a very new field of math, as I mentioned before. The term tropical was coined by French mathematicians in honor of the Hungarian-born Brazilian computer scientist Imre Simon. There was some early work on tropical geometry in the 1980s and 1990s, and there was a push to lay the foundations of the field in the early 2000s. Tropical curves and varieties are the geometric objects that are obtained by plotting the domains of linearity of tropical polynomials. So I'll say a little bit more about what I mean by that on the next slide. Okay. So first here is an example. So let's take the tropical polynomial max of x comma y comma 0. So we want to associate some geometric object to this tropical polynomial, and one way to do so is to think about how this tropical polynomial behaves. So this is defined on the xy plane, and so this picture down below you should think of as living in the xy plane, and we can ask the question, on what points in R2 does the term x dominate over y and 0? In other words, so let me spell out the question. For which points, let's say x, y in R2 is x bigger than y and x bigger than 0. Right? I'm thinking about in which points is the maximum achieved by x. And if you think about it for a moment, the points in R2 where x is bigger than y and x is bigger than 0 are precisely the points in this region right here. And so that's why I've labeled that region by a capital X. And then if you ask a similar question, but now you ask for which points x comma y in R2 is y bigger than x and y bigger than 0, then with a little thought, you'll see that it is exactly this region in R2. And finally, the points x, y, where 0 is bigger than x and 0 is bigger than y are precisely those points in this region down here. And so that's why I labeled this region by a 0. So these regions that I'm drawing are called the domains of linearity of this tropical polynomial. These are precisely the regions in R2 where one fixed term among these three wins over the other two. Or if you like, these are the regions in the plane where max of x, y, 0 is just a linear function as opposed to piecewise linear. Okay, so given any tropical polynomial, I can associate a object like the one I've drawn at the left simply by partitioning space into regions where the different terms in my tropical polynomial dominate. So if we were to do the same game and plot this tropical polynomial, then we will get this picture inside of R2. Now it's more complicated. This tropical polynomial has 1, 2, 3, 4, 5, 6 terms, and so I have, so my tropical curve is this curve in R2 with 6 different regions, and each region is the region where one term is bigger than all the rest. And of course, tropical curves can look even more complicated, and here are two more examples. Okay, so let me say a little bit more about properties that tropical curves have. And the condition that I'm going to focus on is the balancing condition. So first, there's a characterization of what tropical curves in the plane in R2, what they look like. So a tropical curve in the plane is a finite graph embedded in R2 such that the edges are either straight line segments connecting two nodes. By node, I mean one of these points where lines come together, or the edges can be straight lines going off to infinity. Another property is that all edge slopes are rational. And now, most interestingly, around every node, the zero tension or the balancing condition holds. And so I'm going to say now what we mean by the balancing condition. So let's consider a node of a graph. So I'm going to consider this red node right here. By our hypotheses, the edges adjacent to the node lie on lines with rational slopes. And now we say, so on every ray emanating from x comma y, from our node x comma y, let's take the shortest vector, which has integer coordinates. And now we say the balancing condition holds at x comma y if the weighted sum of these vectors is 0. So if we look at this red point here, then I've drawn in this picture the 3 rays emanating from that point together with their slopes. And the line going off to the northeast has slope 1, 1. Sorry, I have drawn not just the slope, but the shortest vector, which has integer coordinates. So those vectors are 1, 1, -1, 0, and 0, -1. And these vectors add up to 0, and so the balancing condition holds at that red point I've indicated. So, so a tropical curve always has the property that for every node, the balancing condition holds. Okay, so now I'd like to move on to the next topic and say a little bit about what is the Grassmanian. So the Grassmanian, GRKN(R), is the set of all k-dimensional planes through the origin in R to the n. So if that's hard to visualize, let's take this small example. So GR1, 3 of R is the set of all one-dimensional lines through the origin in R3. So here's a picture of lines through the origin in R3, and the set of all such lines is the Grassmanian of 1 planes in 3 space. So the Grassmanian is a fundamental object in algebraic geometry, and we can think about it concretely using matrices. So we can represent an element of the Grassmanian of k-planes in n space by a full rank k by n matrix. And the way we think about our Grassmanian element is we take the row span of the k rows. Each row is a vector in Rn, and together they span a k-dimensional subspace. So you can think of the Grassmanian of k-planes in n space as k by n matrices, if you like. You can think of it as a set of full rank k by n matrices, but we just impose the condition that we consider 2 matrices to be the same if they have the same row span. But anyway, if you haven't thought about the Grassmanian before, it's you won't lose too much in this talk by thinking of the Grassmanian of k-planes in n space as the set of k by n matrices. Okay, so now I want to say a little bit about a third topic, which is total positivity. So this is an area of mathematics whose study began in roughly the 1930s with the study of totally positive matrices. So what is a totally positive matrix? Well, we say an n by n square submatrix is totally positive if all of its minors, and that means determinant of squares of a square submatrix, if these are all positive. So let's do an example. So this matrix 1, 1, 1, 1, 2, 3, 1, 3, 6 is totally positive. And to check that, I can check that first of all, every 1 by 1 minor are positive, right? All of the entries are positive. But then I need to check all of the 2 by 2 matrices. So for example, this 2 by 2 matrix has positive determinant. And this red 2 by 2 matrix has positive determinant. And this one has positive determinant. And then some more. This matrix has positive determinant. This one has positive determinant. This one has positive determinant. Okay, there's several more 2 by 2 minors, which are all positive. And finally, the determinant of the entire matrix is positive. So we check all of those minors, and if they are all positive, then we say that our n by n square matrix is totally positive. However, the matrix 1 minus 1, 1, 1, 2, 3, 4, 5, 6 is not totally positive. We can see that already because this entry -1 is not positive. So a given n by n matrix actually has 2 n choose n minus 1 minors. So that is a lot. I mean, if as n grows, this number of minors grows very fast. So it's not very efficient. So if you're trying to check whether a matrix is totally positive, it's not very efficient to check all 2 n choose n minus 1 minors. So a natural question is, how many minors and which ones do we need to check in order to deduce that M is totally positive? Okay, so that question is completely understood, and it has a very nice answer, which I won't go into. But now I want to switch gears a little bit and talk about something called the totally positive or totally non-negative Grassmanian. Now, just to give a little bit of background, in the 1990s, Lustig initiated the study of total positivity in Lie theory. And then in the 2000s, Postnikov initiated the study of the totally positive Grassmanian. Okay, so I want to define what that means. So given a full rank K by N matrix A and I, a K element subset of the numbers 1 through N, we say that the Plücker coordinate P sub I of A is the minor of the K by K submatrix of A in column set I. So I'll show an example in a moment. But first, let me just define the totally positive Grassmanian. So we say that A lies in the totally positive Grassmanian, GRKN, greater than 0, if all of its Plücker coordinates are positive. And for the mathematicians in the audience, I just have a footnote to say, as before, we consider 2 matrices to represent the same point in the Grassmanian if their row spans are the same. Okay, so let's look at a little example. Here is a 2 by 4 matrix A. This represents an element of the Grassmanian of 2 planes in 4 space. So it's a 2 by 4 matrix, and I think about the corresponding Grassmanian element as the row span of the 2 vectors, the 2 row vectors that you see here. So now let's compute some Plücker coordinates. So there are going to be 4 choose 2 is 6 Plücker coordinates, and P12 of A, by definition, is the determinant of the submatrix in columns 1 and 2. So that's 1. The Plücker coordinate P13 of A is, by definition, the submatrix, the determinant of the submatrix in columns 1 and 3, and this is 3. The Plücker coordinate P14 is the determinant of the submatrix in columns 1 and 4, so that is 2. The Plücker coordinate P23 is the determinant of this submatrix. This has determinant 0 minus -1, which is 1. The Pluker coordinate P24 is the determinant of this submatrix, which is 2. And finally, the Pluker coordinate P34 is the determinant of the submatrix in columns 3 and 4, which is -2 minus -6. So that is 4. Okay, so we've computed all 6 Pluker coordinates, and all of them are positive. And so what that means is that A lies in the totally positive Grassmanian of 2 planes and 4 space. So, so again, a natural question is, how many and which of the n choose k Pluker coordinates do we need to test if we want to determine whether a real k by n matrix A lies in the totally positive Grassmanian? Right? We don't want to have to test all n choose k Pluker coordinates, but the question is, which ones and how many do we need to test? Okay, so let's just talk about 2 by n matrices, because here I can explain the answer in a very elementary manner. Okay, so recall that if I is a 2-element subset of the numbers 1 through n, the Pluker coordinate piece phi of A is the minor of the 2 by 2 submatrix of A in column set I. And we want to know which Pluker coordinates should we test to verify that all Pluker coordinates are positive. Now, the first helpful thing to keep in mind here is that there is a relation between Pluker coordinates. And in the case of 2 by 4 matrices, this is what it looks like. So let me actually just quickly write down the Pluker coordinates we computed before. Now what I'm claiming here is that the Pluker coordinate P13 times P24 is P12 times P34 plus P14 times P23. So let's just see if that's true. So P13 is 3, P24 is 2, P12 is 1, P34 is 4, P14 is 2, and P23 is 1. So 3 times 2 is 6. And on the right-hand side, we have 4 plus 2, which is also 6. So this is true, at least in this very small example. Let me show a little mnemonic which explains, which is a good way to remember this Pluker relation. So what I have here is I've drawn a quadrilateral, and I've labeled its vertices by the numbers 1, 2, 3, and 4 in clockwise order. And let me think of Pluker coordinates as being identified with sides and diagonals of this quadrilateral. So we can think of P12 as the side between 1 and 2. We can think of this P23 as this side, P34 as the label of this side, P14 as the label of this side, P13 as the label of this side, and then of course we also have the other diagonal, which we would think of as P24. And now when we've drawn our picture like this, the Pluker relation P13, P24 equals P12, P34 plus P14, P23 is saying that the product of our diagonals is the sum of the products of opposite sides of the quadrilateral. So this is a nice, easy way to remember the Pluker relation. And the same thing holds, the same relation holds if I replace my quadrilateral labeled 1, 2, 3, 4 with a quadrilateral labeled by I, J, K, and L, where I is less than J is less than K is less than L. So, yeah, so there's exactly the same Fluker relation associated to this slightly more general quadrilateral. Okay, so now let's think about the implications of this Fluker relation. One thing that it tells us is that if I know that P12 is positive, and P23 is positive, and P34 is positive, and P14 is positive, and if I also know that P24 is positive, that implies that P13 is positive, because I can express P13 as the right-hand side divided by P24. Similarly, if P12, P23, P34, P14, and P13 are positive, then so is P24. So, so in other words, if I know that the Fluker coordinates associated to the yellow sides and diagonals of my quadrilateral are positive, then the Fluker coordinate associated to the crossing diagonal is also positive. Okay, so now let's talk more generally about 2x(n) matrices. So I already mentioned this previously. If I have A less than B less than C less than D, then I have exactly the same Fluker relation corresponding to the sides and diagonals of this quadrilateral. Okay, so now let's consider an arbitrary triangulation of an n-gon. So here I've shown an 8-gon, and I've labeled, I've chosen a particular triangulation, and I've labeled all its sides and diagonals with Fluker coordinates. So it's a simple fact of geometry of triangulations that if we start from an arbitrary triangulation, we can get to any other triangulation by performing a sequence of flips. And what do I mean by a flip? By a flip, I mean if we start with a quadrilateral which is triangulated in one way, then I can replace it by the same quadrilateral but triangulated the other way. So a flip is a local move which takes me from one triangulation to another triangulation which is nearly the same, but I've just taken a small quadrilateral and changed which was the diagonal inside it that I wanted to consider as part of my triangulation. Okay, so given an arbitrary triangulation, we can get to any other triangulation by performing a sequence of flips. And every time I perform a flip, there's a Fluker relation that goes along with that flip. Now, a consequence of that is that we can express the label Pij of an arbitrary diagonal as a Laurent polynomial with positive coefficients in the Fluker coordinates from our starting triangulation T. So to say a little bit more concretely what I mean, let's start from this triangulation T, and suppose that I want to understand the Fluker coordinate P58. Right, so this diagonal P58, it does not lie in my triangulation, but what I'm saying is that if I want to understand the Fluker coordinate P58, I can apply a series of flips to go from my triangulation T to some other triangulation which contains 5/8. And if I keep track of the Fluker relations associated to all of the flips that I perform, at the end of the day, I will be able to express the Fluker coordinate P58 in terms of the Fluker coordinates labeling T. And in fact, this expression will be a positive expression. It's going to be an expression with positive coefficients. And so the upshot is that if the Pluker coordinates labeling T are all positive for my matrix A, then so are all Pluker coordinates of A. So one way, one common terminology for this criterion is that T gives a positivity test, right? Giving a positivity test means that it's a collection of Pluker coordinates which I can check, and if they're all positive, it implies the rest of the Pluker coordinates are positive. That's what we mean by positivity test. Okay, so the recap of what we've just seen is that if we want to test whether a 2x n matrix A is totally positive, then what we can do is draw any triangulation of the n-gon and label its diagonals by Pluker coordinates. Then, to test whether A is totally positive, it's enough to check whether the Pluker coordinates labeling T are positive. So for a 2x8 matrix, I don't have to check all 8 choose 2 Pluker coordinates. I only have to check the Pluker coordinates shown in this triangulation. Okay, so this is a very nice and concrete way of understanding elements of the positive Grassmanian of 2 planes in n space. If K is bigger than 2, we can still understand positivity tests for the Grassmanian of K planes in n space, but now we have to work with something called Plato graphs due to Postnikov to replace the triangulations that we used in the GR2n case. And I also want to say that there's actually a very general framework for understanding questions of total positivity, and this is the theory of cluster algebras due to Fomin and Zelevinsky. So in particular, the Grassmanian has a cluster algebra structure. This is work of Scott. Okay, so now I want to finally start to explain what all of this has to do with shallow water waves. So again, this is a picture of shallow water waves at the beach. Okay, so first, let me just say a little bit about solitons. So a soliton, or a solitary wave, is a self-reinforcing wave packet that maintains its shape while it propagates at a constant velocity. So these were first observed in 1834 by John Scott Russell. So in 1834, Russell, who was a Scottish naval engineer, described the following phenomenon. So he said, "I was observing the motion of a boat, and the boat suddenly stopped, but not so the mass of water in the channel which it had put in motion. It accumulated around the prow of the vessel in a state of violent agitation, then suddenly leaving it behind, rolled forward with great velocity, assumed the form of a large solitary elevation, a rounded, smooth, and well-defined heap of water, which continued its course along the channel, apparently without change of form or diminution of speed." And he goes on, "I followed it on horseback and overtook it, still rolling on at a rate of some 8 or 9 miles an hour, preserving its original figure some 30 feet long and 1 foot to 1.5 feet in height. Its height gradually diminished, and after a chase of 1 or 2 miles, I lost it in the windings of the channel. Such was my first chance interview with that singular and beautiful phenomenon, which I have called the wave of translation." So these are the kinds of waves that the mathematics I'm about to describe has to do with. Okay, and the more formally, the solution, the waves that I'm going to describe arise as solutions to what's known as the KP equation. Okay, so here is the KP equation. It's a equation in 3 variables, x, y, and t. X and y are spatial variables. T is the time variable. And this equation was proposed by Kadomtsov and Pietviashvili in 1970 in order to study the stability of the one soliton solution of the KdV equation under the influence of weak transverse perturbation. It has many soliton solutions and is used as a model for shallow water waves. So here is a picture of what one such soliton solution of the KP equation looks like. So this is a Mathematica simulation, and you can see from this picture that it looks like there are 3 different waves coming together and meeting at a point. And we should think of this as living in the XY plane, and this is a picture at a particular time t. Now the solutions can be much more complicated than the one shown at the left, and at the right-hand side is another soliton solution. And the parameters in the solution at the right were chosen to make the waves look very thin and tall. Okay, so now how should we visualize soliton solutions to the KP equation? So first, every element of the real Grassmanian gives rise to a corresponding soliton solution to the KP equation. We studied these in joint work with Yuji Kodama, and our approach to studying them was to fix the time t. This is like taking a snapshot of configuration of waves, and then we draw its contour plot. And what do I mean by the contour plot? This is a piecewise linear curve in the plane, which approximates where the waves have their peaks. So the picture, the contour plot I would associate to the solution at the left is this piecewise linear curve right here. So now there's a lot of natural questions. What contour plots can arise? What do they look like if time t is very small or very large? How do they evolve over time? And if we're shown a contour plot for a given time t, if we're given a snapshot of this kind of configuration of waves, can we predict what happens when the time t changes? So these are some of the questions that we were thinking about. Okay, so in order to tell you more about our work, I want to review the definition of Grassmanian. Recall that the Grassmanian of K-planes and n-space is the set of all k-dimensional subspaces of an n-dimensional real vector space, and we can represent elements of the Grassmanian by full-rank k by n matrices. And recall that given I, a k-element subset of 1 through n, the Plücker coordinate P sub I of A is the minor of the I submatrix of A. And remember, what I mean by that is take your k by n matrix A, and now given this k element subset I, look at the columns of A located in positions capital I. That will give us a k by k submatrix, and now we take its determinant, and that is P sub I of A. Okay, so those are the Plücker coordinates. And I defined before the positive Grassmanian to be the subset where all Plücker coordinates were positive. Similarly, we say that A lies in the totally non-negative Grassmanian if the Plücker coordinates are all non-negative. Okay, so now I'm just going to kind of tell you a recipe for getting a solution to the KP equation. So given an element A, this is a full rank k by n matrix, we can construct what's called a tau function and then use that to construct a solution to the KP equation. And this is following works of Sato, Hirota, Satsuma, Freeman, Nemo, and others. And let me just show you what such a solution looks like. So first, we're going to fix some real parameters, kappa j, which are ordered. These parameters are going to help to determine what are the slopes of the different wave, like solitons in our solution. And now we'll define this exponential function, e sub j of t1 through tn, to be e to the following expression. And this expression is a linear combination of the ti's, and the coefficients are powers of kappa j. Okay, so this is some exponential function. And now if j is a k-element subset of the numbers 1 through n, we define e sub j to be essentially just the product of the exponential functions ej1 through ejk times this sort of constant in terms of the kappas. And now the tau function is a sum of exponential functions. So we've got a sum over all k-element subsets of 1 through n. And we're summing together the exponential functions weighted by the Plücker coordinates of A. Okay, so A is this element from the Grassmanian. So we have a bunch of Plücker coordinates, and they come in as exactly these coefficients here. Okay, so that's what the tau function is. It's this linear combination of exponential functions. I realize this is a little bit technical, but you don't need to kind of internalize this definition. It's just to sort of be honest about what solutions we're studying. Okay, so up here again is just the notation that I had on the last slide, our definition of the tau function. And now, using the tau function, we can construct a solution to the KP equation, and that's just a simple transformation of the tau function. So recall in our tau function, we have these n variables t1 through tn. Let's let x be t1, y be t2, time t will be t3. Treat the other t sub I for the constant. You can make them 0 if you like. And then u sub a of x, y, t, which we define to be the second derivative with respect to x of the log of the tau function. That is a solution to the KP equation. So this was proved by Freeman and Nemo, and this is basically what we're using as a black box. We will be studying solutions to the KP equation which are of this type. So they depend on our Grassmanian element A. They also depend on some fixed parameters, and from that data we get a solution to the KP equation. So now one thing that I'd like to point out is that if the Plücker coordinates are all non-negative, this solution is regular everywhere. In other words, it never blows up. So you see, if this tau function were ever 0, then this log wouldn't make any sense. And our solution wouldn't be regular. However, when we require that our Plücker coordinates are all non-negative, then the tau function is always positive and this solution is always regular. And so it's very nice to restrict attention to solutions of the KP equation coming from the non-negative Grassmanian. Okay, so now let's think about how to visualize soliton solutions to the KP equation. So recall that a solution is defined in terms of the tau function, which is a sum of exponentials. Now at most points, x, y, and t, our tau function will be dominated by exactly one term. One exponential will be bigger than the rest. And at such points, our solution, u sub a of xyt, will be close to 0. And so we define the contour plot to be a subset of the xy plane where 2 or more terms dominate tau sub a of xyt. This approximates the locus where our solution takes on its maximum values. And if we've chosen our kappas, our kappa i's, to be integers or even just rational numbers, then actually it's easy to see that this contour plot is in fact a tropical curve. Okay, so the contour plot that we are using to approximate our sort of wave formation is a tropical curve. So that's the first, this is where tropical geometry enters into the picture. So I want to label regions of the contour plot by which exponential term dominates the rest. Okay, so in each of my, so in this example, there are exactly 3 exponential terms, and there are exactly 3 regions. And what this picture communicates is that for this solution, so this is actually a solution coming from an element A in the Grassmanian of 1 plane sub 3 space. In this in this soliton solution to the KP equation, in the xy plane, there are 3 different regions where each of the exponential terms dominates, and that's what I'm showing here. Okay, so we are going to label regions of the contour plot by dominant exponentials. One term, e sub I, dominates u sub a in each region in the complement of our contour plot, and so we label the region by the dominant exponential. Okay, now what do these soliton solutions look like? So generically, interactions of the lines are trivalent, like this, or they might form X crossings, which are sort of like 2 lines which pass over each other without interacting. And if 2 adjacent regions are labeled E sub I and E sub j, then it's not hard to see that the K element subset J is nearly the same as the K element subset I. They differ by swapping out one index from capital I and adding in another one. So yeah, so an example in this picture, we've got a dominant exponential here, and the dominant exponential in the adjacent region is E4, 5, 7, 8. And so you can see that these 2 4-element subsets differ by swapping 7 and 9. And then it's a fact that the line between those 2 regions has slope kappa I plus kappa j. So this line here has slope kappa 7 plus kappa 9, and so we label that line by this pair of integers. So now we want to reduce all of this to combinatorics, and so we're going to associate a graph to our contour plots by forgetting the lengths and slopes of the edges, and moreover by marking a trivalent vertex either black or white based on whether it has a unique edge down or up. So there's going to be 2 kinds of trivalent vertices, and they will either have, so all of this is in the xy plane. So I'm going to think of down and up as meaning towards y is negative infinity or towards y is positive infinity. So so this kind of configuration I would think of as having a unique edge going down, and this kind of configuration I would think of as having a unique edge going up. And so I'm going to label these 2 configurations using black and white vertices. And so if we do that in this picture, for example, this should be black, this should be white, black, white, black, and so on. And then we get this picture at the right, which this picture at the right, I'm now just thinking of as a graph. I'm not keeping track of the lengths and slopes of edges anymore. Okay, so a natural goal is to classify these kinds of graphs. So let me start by forgetting even more information. I want to associate what we'll call a generalized playback graph to every soliton graph by doing the following. So for every unbounded line soliton, I and j, headed off to y is plus infinity. So for example, this is a line headed off to y is plus infinity. I will, in my playback graph, I will label the boundary vertex here by the bigger of the two numbers. Right, so this was labeled by 1 and 5, and now I'm going to label this vertex by 5. And similarly, for every unbounded line soliton heading off to y is negative infinity, label the incident boundary vertex by I. So for example, this line here is headed to y is minus infinity, so I will label the corresponding vertex by 1. Okay, so when we do this, we get the graphs that I've drawn at the right, which we've now forgotten all of these labels of edges, and we just now have labels on the boundary. And this is what I call, this graph over here is what we call the generalized playback graph. Now the first theorem is that passing from our soliton graph to the generalized playback graph doesn't lose any information. What do I mean by that? Well, we can reconstruct. So from the picture at the left, we can reconstruct all the labels at the right by doing a procedure called following the rules of the road or zigzag paths. And so what we're going to do is we'll start from each boundary vertex in turn. We'll take a path along the graph, turning right at black vertices and left at white vertices, and then label each edge along the trip with an I, and each region to the left of the trip by I. So, for example, if I start at 1, I will take this unique edge here, and then I get to a black vertex, so I turn right. Then I get to a white vertex, so I turn left, then right, then left, and then right. And now we do the same procedure starting from 2. I label this 2, and then I turn left, and then I turn right, left, and right. Now we start at 3. We label 3, then we turn left, right, left, right. Then start at 6. Turn left, turn right, turn left, turn left. And so in this way, if I follow this procedure, at the end of the day, I will have completely reconstructed all of these labels along my edges, which recall we're encoding the slopes of the line. And why does this procedure work? Well, at the end of the day, it works precisely because the contour plot is a tropical curve and it has the balancing condition around every vertex. And so this gives us a way to identify the soliton graph with this much simpler and completely combinatorial object, this generalized playback graph. Yeah, so there's a lot more that we can say about soliton graphs more generally using the positoroid cell decomposition of the TNN Grassmanian. So this is the partition of the TNN Grassmanian into pieces based on which Plücker coordinates are strictly positive and which are 0. And that uses some objects called Lie diagrams. So Postnikov showed that positroid cells, these pieces of the TNN Grassmanian, are in bijection with certain tableaux called Lie diagrams contained in a k by n minus k rectangle. And so this gives a way of labeling cells of the TNN Grassmanian by these objects called Lie diagrams. And so a sort of general question is, if you start from an element A, from some positroid cell in the TNN Grassmanian, what can we say about the corresponding soliton graph or contour plot, right? So if I start from an element in a positroid cell of the TNN Grassmanian, what can we say about the shapes of the contour plots associated to its corresponding solution of the KP equation? And the sort of meta theorem is that which cell A lies in determines completely the asymptotics of these soliton graphs as time goes to plus or minus infinity, and also y goes to plus or minus infinity. And we can use these Lie diagrams labeling the cell. So I don't have much time left, so I think I'm not going to go into details on this next bit, but I do want to just mention that that we have a very pretty combinatorial procedure, which, starting from this combinatorial objective Lie diagram, computes the contour plot obtained from the soliton solution of the KP equation when time goes to negative infinity. And it's this sort of completely algorithmic game where we start from our Lie diagram and gradually transform it until we get the contour plot. And this is, so this is the output of our sort of combinatorial procedure. And this is the Mathematica simulation of the same contour plot. So you can see that they're the same. There's other questions that we can ask and answer. So one natural question is about the inverse problem. Given a time t, together with the contour plot of the soliton solution of the KP equation, can we reconstruct the point of the TNN Grassmanian, which gave rise to the solution? This is an important question to answer, because if you can reconstruct the point of the TNN Grassmanian, then you can figure out what will happen as time evolves. And so we can answer this question in a fairly general situation. One of our answers uses very much this notion of positivity tests to do with the Grassmanian. Another natural question is about when these soliton solutions are regular. Remember, I mentioned at the beginning that if you start from an element in the Grassmanian, which lies in the totally non-negative part, when all Plücker coordinates are positive, then our solution is regular for all times t. It turns out the converse is also true. In other words, if you start from a point in the real Grassmanian and you find the corresponding solution to the KP equation is regular for all times t, then in fact your point A must have come from the TNN Grassmanian. So the recap is that tropical geometry and the positive Grassmanian, topics from pure mathematics, turn out to beautifully describe various phenomena related to soliton solutions of the KP equation, or in other words, shallow water waves. Here, wave patterns get approximated by tropical curves, and combinatorial objects such as Lie diagrams, which encode the structure of the Grassmanian, allow us to characterize the contour plots when time goes to plus or minus infinity. We can also address the inverse problem. So given a snapshot of a wave formation at a time t, we can understand what will happen as time evolves. This is a picture here of two snapshots from that same beach in Mexico, taken in close succession, and one can understand combinatorially how these wave patterns interact and how they change. And I'll just close by mentioning that the positive or totally non-negative Grassmanian is linked to multiple real-life phenomena. As we've seen in this talk, it's related to soliton solutions to the KP equation, which in turn models interaction patterns of shallow water waves. In earlier work with Quartile, we studied the asymmetric simple exclusion process, a statistical physics model for traffic flow and protein synthesis. Also found a mysterious link with the TNN Grassmanian. This asymmetric simple exclusion process is a model for particles hopping and repelling each other on a one-dimensional lattice. And in yet a third direction, work of Arcani Hamed, Bourgelat, Cachazo, Gontrov, Potnikov, and Trinka studied scattering amplitudes in n=4 super Yang mills. This has to do with the scattering of elementary particles, and found that this theory is also closely connected to the TNN Grassmanian. So I'll just end with this sort of question, why? Why is the TNN Grassmanian connected to real life, and in particular these three topics? And finally, here is a picture of some soliton solutions to the KP equation. So thank you very much for listening, and I will stop here.